What's up, world? Welcome back to another tutorial. Today we're going to be talking about maths. Don't get scared. Don't you leave. Maths is fun in graphics. It's the fundamentals of graphics and game engine programming. You got to know math, man. It's just how it works. But anyways, we're going to be talking about translation, rotation, and scaling of our game object, our quad on the screen right now. In order to do so, we're going to talk about matrices. And what the heck matrices have to do with programming and why linear algebra is so freaking fascinating when it comes to stuff like this. So get excited. I'm excited. Go ahead and hit that thumbs up button, the like button, if you like this. And also subscribe if you want more and more and more videos. I'll keep pumping them out, promise. Yeah, let's go. All right, before we get started in coding, I want to talk a little bit about theory of the mathematics of moving around objects in space in three-dimensional and two-dimensional planes. Let's talk about screen space. We've already talked a lot about screen space, but let's talk about objects in screen space. So you'll see we have our quad from our last episode placed at these 4 vertice positions. Say we wanted to scale that down, right? We wanted to move it down so that it doesn't take up so much of the screen space, right? And maybe say we want to rotate it. So we've rotated it, and now we want to move it after we've rotated. So we want to create this whole entirely new position. How do we do that? How do you do that with objects if we just have a vertice array, right? Because as of right now, we just have the vertice array. So if we wanted to do this, we would need to pass in every one of these manually updated positions in space to our vertice array. That is unrealistic. It's hard to do. You might be able to do it. If you want to do it that way, you totally can. You can figure it out. I'm not going to do it that way because there are a lot better ways, especially since the GPU knows how to do multiplication. Now that's kind of a hint into what I'm going to be talking about. I know I said it before. Let's get into it. Matrices. These gorgeous mofos, you'll see we have a 1x4, a 3x2, a 2x3, a 3x3, and a 4x4 matrix. And we want to do operations with these things. What do these mean? So the reason graphics and machine learning and all other computational algorithms out there use matrices is because they're really fast. You can do matrix or multiplication operations on matrices insanely fast. A lot of times you'll see matrix operations with formula in them where they don't look just like numbers, they're more so calculations, and that's because they act as an operation. So you could take one matrix, multiply it by the operation matrix, and get an entirely different matrix at the very end. So what's really cool about matrix operations, especially with graphics, is that we could take a 1x4 matrix, multiply it by a 4x4 matrix, and you see I have the 1x4 matrix on the left and the 4x4 matrix on the right. If we multiply those together, we get a 1x4 matrix returned. And I'm just going to tell you a little bit about math and linear algebra and why this is. So you'll see that the columns and the rows, so the column of the original value and the row of the operation, those are equal, right? So those are 4 and 4. If those were 3 and 2, this would not work. You cannot do operations on matrices with invalid numbers like that. But you'll wonder, oh, well, the new value has 1x4. Where does that come from? Well, right here. This is where the 1x4 comes from. This is just a really quick way to remember exactly how. If you actually do the multiplication out, you'll notice this comes out to be a 1x4. Anyway, just notice it goes out to a 1x4. Now, why is this useful? Why in the hell are you telling me this, Mr. Tutus? Well, I'll tell you why. Because we can move the object around. So I'm going to show you using an example of translating a position. Take this vertex, for instance. We want to take it and we want to move it around, right? So look at the origin. The origin is at 0, 0, 0, 1, that being x, y, z, w. The w coordinate is the homogeneous coordinate. You'll know that the vertex shader returns a float 4. The float 4 has that W component that acts as the homogeneous component, and it's not important for you to know really off the top of your head right now. I might talk about it in the future. Actually, I'm probably going to talk about it in the future because we'll need to go over projection matrices. Anyway, we have X, Y, Z, W, the Z pointing at your nose, and X, Y just kind of in the normal coordinates that you know of. So we want to move this vertex around. What do? Let's take this position, this matrix this position that I've turned into a matrix, so 1x4 matrix, and let's multiply that by a move operation or a translate. They call it translate operation. You'll see that the bottom row right now has the translation number. So the x is 0.75 and the y is negative 0.75. If I were to take my origin position and multiply it, the 1x4 by times the 4x4 position, matrix operation, you'll see I get a new position. And we've moved our vertex down to the bottom right. And that's because they're super fast operation. We didn't even really need to do much. We just wanted to move it 0.75 units in the right and down. So that's why they're so awesome. But what makes these even more freaking spectacular, sorry if I'm being annoying, but I'm getting pretty fired up. These things can be done sequentially. So take, for instance, this object, right? Let's show you why we're not passing in we're updating the vertice array in the beginning. It's ridiculous. We don't need to do that because what we can do is we could take our original position and we can multiply it by the translation matrix and we translate our object. Then we take that whatever comes out from that and multiply that 1x4 times the rotation matrices. We'll do the Rx, the rotation of X, the rotation of Y, and the rotation of Z. All of those need to be taken into account. Once we have that, we can take that 1x4 matrix and multiply it by the scaling matrix, which will scale it down. That was 3 simple matrix multiplication operations done on the original position to now give us our new position in space. That's why matrices are so amazing. And that is why we're going to start coding that right now. Alrighty, so back where we left off, we have this nice quad on the screen. Let's get moving him around. He wants to move around. He's got a lot of energy, just pent up energy, and he wants to move around. So let's start talking about model constants. Model constants are a way of transferring movement information on our model or our game object to the GPU to do those matrix operations, and the GPU will do those for us. So just to kind of tell you what the heck that means, show you what that means, I'm gonna give you an example. So up here at the top of the game object, I'm gonna put var delta position. And what that's gonna represent is the change in the position of our object. Now that's gonna be at float 0. Underneath the initializer, I'm also going to put a function called update. And that update will take in a delta time. So this is kind of like the game loop. Each game loop will have a delta time associated with it. That's usually real time. In our case, we're just going to use 1 over basically 60. And that will be like every 60th of a second. But we'll optimize that. We'll do that in the future. We'll do more game loop optimization. Anyway, now we have our update function. Let's go back out to our renderer class and let's call it. So right now we're calling player.render. Right above that, we're going to call player.update with our new delta time, which will be 1 divided by, cast this as a float, and then you can go view.preferred frames per second. So this right now will return 60. It's defaulted to 60. You can put that wherever you want, but that will return 1 over 60. So we're going to go to our update function in our game object, and we want to update our delta position. So to update our position, what I'm going to do to kind of make it go back and forth, just follow along, I'm going to create a variable called time above our update, and I'm going to set that equal to 0. Now what I'll do is every time update's called, I'm going to change time to be plus equals delta time. So our time's just going to keep ticking up by that amount. So 1 over 60. Now, what does all this mean? We have our delta position, time. So let's do delta position plus let's do equals the cosine of time. So that way that our delta position goes up and down, and just to kind of test this out to make sure, I'm going to print out our delta position, and we should get a value between -1 and 1 because that's how cosine works. Trig, bro, and get used to it. It's all code is. Look at that. -1 and goes right back up, you see? So now that we have this kind of up and down nature, we can use that because screen space is maxes out at 1, right? So already set up. Let's just update the position of our game object. So to do that, let's go back to our shader. Let's talk a little bit about our shader. So our shader takes in this vertex in and the position. Let's create a little struct over here. Actually, I'm not going to create a struct yet. I'm just going to do this. Let's create a new parameter, and I'm going to say that's a constant of a float, right? Because we have our delta position is a float. And I'm going to take in the reference to the delta position. And that will be at buffer. Let's do buffer index 1. So at delta position, buffer index 1, we're going to take in our delta position. Now our rd.position is going to be updated. So rd.position.x plus equals the delta position. So as the delta position increases, we're going to increase our position.x, right? And we haven't even touched those vertices. Never touched those vertices in the original array. Those are already at whatever value they're at. So the delta position is now updating our position x of our object. Now back in our game object, inside of our doRender loop, let's go ahead and attach that. So we can call render command encoder.set vertex bytes. Now, real quick, I'm just going to tell you why I'm using vertex bytes as opposed to making a whole buffer for this float. I forget the value. I think it's like 4 megabytes is what a buffer can, like you don't want to create a buffer unless you have a value over 4 megabytes or 2 megabytes. I'm sorry, I don't know what it is off the top of my head. But once you're over that cap, then you'll want to start creating buffers. If you have 400,000 vertices that you want to pass to the GPU, use a buffer. If you just have a couple bytes, well, you can just pass the reference to those bytes really easy. And you can do that simply by calling render command encoder.set vertex bytes. That will still set them at the buffer of the index that you choose. So in our case, we want to pass the reference to the delta position. So we're just going to pass the vertex bytes of delta position all the way down. It says ambiguous reference to member blah, blah, blah. Okay, I guess, yes, okay. And then what I need to do here is go memory layout of, it's a float.stride. And remember how I created the sizable? Let's go ahead and go back to our types right here. And I'm just going to extend float as well. So above here, I'll put just a float. So I don't need to do that memory layout thing. See, our float's now extending sizable, so it should have these properties assigned to it as well. So back here, I don't need to do memory layout.stride. I can just go float.stride. And then the index is going to be at 1 because that's where I placed it in my shaders, right there at buffer 1. So now if I go ahead and press play, hopefully awesome things happen. If they don't, well, we'll figure something out. I promise. So, ooh, look at that. Our positions are being updated simply by passing these model constants. Now, this doesn't make any sense. We're not going to pass one variable for every single. Right now, we're passing just this simple delta position x variable. It's just a float. We don't want to do that. We want to make this a little bit more dynamic and a little bit more easier to understand because, you know, we're dealing with position scaling and rotation. You know, like rotation is going to get a little complicated. And so let's make this a little bit better. So what we're going to start making is what is known that's known as the model matrix. Okay, so the model matrix will contain the multiplication of all of our matrices together. We have a position, a scale, and a rotate. Our model matrix will contain all of that, and I'll show you what I mean. So back in our node, let's go back to our node, okay? And I'm going to create a variable, and I'm going to call it position, right? And the position will be a float 3 because it will be a float 3 in space, in 3-dimensional space. And I'm going to set that equal to the origin, which is at 0. Now that we have our position, we can create our model matrix. Our model matrix will have, so var model matrix, okay? And that will be a float, that will be a matrix float 4x4. Inside, I will say var model matrix equals matrix. Now we need to set it to the identity. If you don't know what the identity is, it's just 1. It's setting the matrix equal to 1. It's literally 1, like multiplying 2 by 1, you get 2. Matrix, multiply any matrix by the identity matrix, you get that same exact matrix in return. And then I'm going to return that model matrix. Okay, so really this model matrix isn't doing anything right now. It's just a 1. So if we were to multiply our position by 1, we're going to just get our position back. But we want to do those translation rotation scales. So all I want to be able to do right here is say model matrix dot, let's say translate. And when I say translate, doesn't mean figure out English from French and German. It doesn't mean translate a language. It means move. So model matrix dot translate means translate the position, move the position. Translate, and I want to pass in, well, let's say the direction we want to go, and that will be a float 3, which will be our position, right? So this will be our, like where we want to end up. But we don't have this model matrix dot translate right now. Okay, this is going to come back with an error. It's like, I don't know what the hell you're talking about. So what we need to do is we need to create the translate function. So up in our game engine, I'm going to create a new group, and I'm going to call it our maths. I say maths because I've watched a lot of British people on YouTube, and they say math. So I'm going to say maths too. I'm going to create a new file in that folder, and I'm going to call it just math. And we'll probably make this a little bit better in the future. Nah, that sounds good. All right, so here's our math. Math will contain certain functions, such as our translate function. Okay, so let's go back. Let's talk about it real quick. Inside of our node, we have model matrix dot translate. Model matrix is a matrix float 4 by 4, which means we can extend functions of the matrix 4 by 4. So in math, right here, I can go extension float 4 by 4. Well, matrix float 4 by 4, right? Matrix float 4 by 4, and I can create functions in here that matrix float 4 by 4 can do. In order to do certain, operations on myself. So say I want to say model matrix dot translate. I'm translating on myself. So you need to start that with mutating func. So it'll be a mutate myself function, and I'm gonna call that translate. And just like before, you saw I put in direction, right? And that will be a float 3. So whatever direction we want to go, everything should build just fine. And as a matter of fact, if I go back out to my game object, or my node, excuse me, you'll see that everything compiles, and that's because it knows now that there's a translate function that takes in the direction and position. Cool. Now all we need to do is implement it, right? So we need to create our model matrix, which is all of our translate, rotate, and blah, blah, blah combined. So let's go back to our maths, and let's create this translate function. Now I'm going to do this from memory. I believe it goes a little bit something like this. First thing first, I'm going to create my result as a matrix identity float 4 by 4. And then I'm going to return the result. No, I'm not. I lied to you. I'm going to say self, which is me as a matrix. I'm going to say self equals matrix multiply. I'm going to go self times result. Okay, so remember how I said you can take other matrices and multiply them by each other? That's what I'm kind of doing here. I'm saying I want to multiply myself by whatever I create here. And right here is noted by the translation matrix. And on the screen right now, you should be able to see some pretty sweet diagram of the translation matrix. And you'll notice that it only takes up the bottom row, right? So let's do the bottom row. So the way you would do this is go result.columns. So we need to set the columns equal to, and then each column is made up of a float 4, obviously, because it just goes float 4, float 4, float 4, float 4. Keep in mind, this is column major. If you know what that means, you know what it means. If you don't know what that means. Whatever. Maybe I'll talk about it in the future. If you want to learn about it, I'll teach you. Khan Academy is the shiznit, though. Just letting you know. All right, so I'm going to create 4 of these because the float 4 matrix float 4 by 4. And I'm going to get rid of this comma. See, so now I'm creating this new thing right here like so. I'm going to create a couple little variables up top. Let x as a float equal direction.x. Let y as a float equal direction.y. Let z as a float equal direction.z. dot z. And that's for readability. Just makes it easier to read. I'm going to create the identity matrix real quick, like so. Make these zeros. So this is the identity matrix. And I'm just going to, literally the bottom row, just X, Y, and Z. And hopefully this is the translation that I remember. I may refer to some notes in just a second for some of these other ones, like rotate. That's a hard one. So yeah, here's our translation function. We're going to take this result. We're going to create this new result to multiply. This is our you can do whatever you want in here, but for the most part, this is already mathed out by smart people. And then back in our node object, we're saying take this 1 and multiply it by the model matrix translation. Now, what do we do with this? We have our model matrix, but where the hell do we put it, right? Okay, I think you're lying to me. It's lying to me. Yeah, it lied to me. So in our game object, let's do this. Let's create, well, not in our game objects, in our types. In our types, I want to create a new struct, and I'm going to call that struct model constants. Don't forget to extend sizable like so. Model constants will consist of a model matrix. This is where we're going to put it, peeps. Yeah. And I'm just going to set that equal to the identity matrix again. So model matrix equals 1. And then back in our game objects, I'm going to instantiate that. Remember last episode when I talked about the mesh and the model constants? This is where it becomes really nice because now they're separated out. So I'm going to create a new variable at the top called model constants, and I'm going to set that equal to a new model constants variable. And now we have our model constants in mesh. I'm going to get rid of delta position now because we don't need it. I'm also going to get rid of this delta position. Well, yeah. So let's just kind of use it though. So we have our model constants, and just like I was passing my delta position into the vertex shader, I'm going to pass my model constants. So right here, instead of delta position, I just go model constants. It won't be this easy, obviously. Back in, now that we're taking in a model constant, we need to do the model constants.stride, which isn't that hard. So we're going to do the whole size of the model constant, which is pretty easy, still less than 4 kilobytes, hopefully. And then back in our shader, let's go ahead and create a new struct here and also call that model constants, just to match it up with the data on the other side. So that will take in a fantastic float 4x4. It's called a float 4x4, the matrix is right here. And I'm going to call that also model constants. No, that's not what I'm going to call it. I'm going to call it model matrix. And boom. Okay, instead of taking in the delta position, I'm going to be taking in a model constants, and then this will be the reference to model constants at buffer 1. So everything's the same. This won't exist anymore. So I'm just going to remove this line and show you some cooler stuff. So back in our game object, let's send the model constants down. So right now we have this model constants, right? And it has an identity matrix set for the model matrix. We want to change that. So underneath our update function, I'm going to create a private function, and I'm going to call that update model constants, because there's going to be other variables we put in here. For now, we're just going to have the basic model matrix, but in the future we'll have more stuff. So I'm going to pass in delta time float. And then I will say in update model constants, I will say model constants dot model matrix equals self dot model matrix. And when I say self dot model matrix, I'm referring to the nodes model matrix, private func, that's the problem. I'm referring to the nodes model matrix right here. It's grabbing this, which we've created with this position. So we can just update the position of the object, right? Am I right? You could just update the position. That's it. We won't even touch this really. This is going to be read-only for the most part. It is read-only for the most part. Stop saying for the most part. It's read-only. So we'll just update our position, and then this will do the magic for us. So back in our game object, let's call this function update model constants, and then we'll pass in the delta time. I'm sorry, we don't need to pass in the delta time right here. I don't know what I was thinking. All we need to do is call update model constants. So after we've updated our positions and whatnot, which let's update our position, self.position equals the cosine of time. Once we've updated our position, we now need to just update the model constant to use that new position in the model matrix. So that's kind of how the flow goes. It goes update the self.position.x equals the cosine of time. That will move back and forth, and this will work just dandy. So there's only one more thing we need to do. We are setting our model constants vertex bytes that have been updated with this position of cosine of time. Okay, I know this is probably a little confusing. Just do it 500 times and it will snap in your brain and you're gonna be a genius, I promise. But you'll see that our self.position.x is being updated to the cosine of time. Back in our freaking shader class, let's go to our shader. All we need to do now is multiply our model matrix. So I'm gonna go model constants. We need to multiply that by the model constants.model matrix times the position. And this order is important as we do these model matrix and view matrix and projection matrix. This is model space, by the way, model space, or model coordinates, I think, is the more professional. They say all sorts of things, but this is the model, because the model moves around on the screen in position, or not even on the screen, just in space. The model will move into space. The view will move the camera in front of the model, and then the projection matrix projects it out. I'm getting ahead of myself, a couple episodes. So just note that we need to do model matrix times the position, not position times model matrix. That order is important. So yes, I'm gonna press play. So now that we're updating our position to equal this, we should get a nice freaking back and forth. Same thing, look at this. We're just updating the position. We're not updating any matrix. There's no matrix updating at all. The matrix, it's kind of just computing itself, which is really nice. But you see, we get this nice back and forth motion. Let's move forward just a little bit and talk about the scaling. Sure, scaling. Rotation, we'll save that one for last because I'm gonna need to grab some code. Let's scale this mofo. So back in our node, let's create another variable and we're gonna call that scale. That'll be a float3. And then I'm gonna set that equal to, well, we want the scale to be a 1, right? Because we don't want it to be 0. If it was 0, it wouldn't exist. We want it to be exactly what it is when we send it in. And you wanna do translate, rotate, and scale. So the last thing we're gonna do is model matrix.scale. And we scale along the axes. You can scale on the x-axis, the y-axis. So if you wanna scale along the x-axis, you're gonna stretch it out this way, right? And then if you want to scale along the Y, you're going to want to scale it this way. And if you want to scale the Z, you'll scale it back and back. So you're scaling on different axes. So if you have a cube, you can stretch it out in whatever way you want, or a ball, you can morph it, whatever. So we're going to say model matrix.scale, and we're going to pass in an axis to scale on, and that will be a float3 as well. But I like pretty code. So, actually, yes, I like, well, no, this needs to be scale. Sorry. So we're going to model matrix.scale, and then we're going to pass in the scale of there. I was thinking ahead of myself. But we don't have the scale matrix. Let's go make it. Go back to the math class. I'm going to just copy this translate because it'll be a lot faster. And just give me 1 second of work. I'm going to go ahead and fix this up to be the scale function. All right, so that was pretty simple. Just note that it looks freaking the same. Look at that. Translate looks very similar to scale, except now instead of these being X, Y, and Z, they're now going up the diagonal. And this is because this represents the scale of the matrice. So now that that's all put together, I'm passing in the axis and updating all this. Just kind of copy that down. Let's go back out to our, let's check the node. Checking, updating the scale. We're scaling with our model matrix. Model matrix already going through. So back in our game object, let's just say self.scale equals float3. So we're going to scale along all axes. And I'm going to say that's the cosine of time. So it'll grow and shrink. Should be pretty sweet looking. Yeah. Let's check it out. Whoop. Sweet. So it kind of looks like it's going off in the distance. It's not. It's just getting smaller as it goes. It just kind of looks like it's going backwards. This isn't 3 dimensions yet. Don't get too excited because we're only translating along the x-axis. Let's do the rotation. Give me 1 sec. Okay, so I'm back and I want to show you the rotation function. So go ahead and go back to your math, and I'm just going to copy and paste it on here. I'm going to create some room so you guys can see. And then I'm going to paste this monstrosity. So I'm not going to explain this. Like I said, I'm not a math major. I just know that I coded what I saw and it worked. So yeah, you're welcome. So this right here, let's see if I can get it all in there. Boom. That is the rotation matrix. We're going to take in the angle at which we want to rotate and the axis. So we rotate just like we rotate scale along the x and y and z. We also want to rotate along the x, y, and z. So if you're rotating on the z-axis, which is pointing at your nose, you're rotating around that axis. If you're rotating around the y-axis, you're rotating around that axis. So everything will spin around that. The Earth rotates on a kind of a y-axis, except it's on a tilt, so it rotates on the x and the y-axis. But that is, we can make a world. That's all I'm saying. We're gonna make the world. It's pretty sweet. So this is the rotation. Copy that down. Check it out. Make sure these are all aligned. I haven't memorized this. I should memorize this. I probably should, but I'm not going to. But I will. But I won't, because it's ridiculous. But this is the rotation. And let's get into using it. So it works pretty much. It's the same exact concept where we have this result, we update all these columns, and then we return this value. So it's working the same way as the other ones. It's just effing ridiculous. There's also quaternions, and we'll get into that in the future too. That's a lot better. But this is the simple rotation factors that we're going to use. So let's take this information and go back out to our node. So in our node, we're going to create a new var called rotation. Float 3 equals float 3, and we don't want to rotate yet, so it'll be a float 3 with the origin of 0, so we're not rotating at all. And then we need to rotate around all 3 axes, the x, y, the z. So I'm going to go model matrix dot rotate around what angle? Well, we have our rotation dot x is the angle, and then the axis will be float 3, 1, 0, 0. That's the x-axis, right? Because this is x, y, z. This is the x. I don't like that. I think that looks ugly. Let's go back to math and create a couple little sexy things. So up here at the top, I'm just going to create a couple variables. So let's create public var, and I'm going to call this the x underscore axis, and that will be a freaking float 3, and I will return, just like so, the float 3 of 1, 0, 0. So that is the x-axis, and that will work just fine. I'm going to do the same for the y and the z freaking axis, because that will be a lot faster. So y and z, save it. I'm gonna remove these lines because that's ridiculous. X, y, z, this is the y right there, and then this one will be the z. X, y, z with a nice little variable. Now watch how beautiful this looks. So instead of doing this, oh, watch it, x underscore axis. Look at how much nicer that looks. You won't find that anywhere else, people. So I'm going to take this right here, and I'm going to copy it 2 more times because we need to rotate separately. If you try to do it all at once, don't do it all at once. It comes out funky because it needs to do it sequentially. X, Y, and Z, and then this will be the Y axis, and this will be the Z axis. Yay. Look at that. We're rotating. We've already set up rotation. Now we just need to do it. Go back to your game object. And let's go self.rotation.z around your nose, like so, like that. I hope that's, yeah, okay, that was ridiculous. Yes, equals cosine of time. Huh. Guess we'll just use that, huh? And let's press play. Really, the rotation.z could just continuously grow, and then it would just keep rotating around. I'm not going to do that. Oh, no. Okay, well, that's kind of cool. Let's make it to a circle. So I can say self.position.y equals the sine of time because that's the y-axis. Well, like the y. Hopefully you know your trig. Please know your trig. If you don't know trigonometry, it's one of the best subjects out there. It's very hard, but very cool. So now we have this nice circle. Woo! That doesn't look nearly as cool. Let's do time. No, that won't do anything. I'll just slow it down. So that you can play with these things and kind of get anything you want. So plus maybe, you know what? I'm gonna invert these. That'll still, no, it won't. I'll just do sine of time and sine of. So if I do the position of x and the y, you can play with these all you want. This is very simple calculations. These are kind of like formula, but we should get this like kind of an x. Yep. You do whatever you want. But look at that. We're placing this thing in space, which means that instead of scaling down, so let's go, last thing I want to do, last thing I promise, is go back to our mesh library and update our triangle. You see right here how we were doing 0.5 all the way down. That's how we were scaling it before. Well, we have a scale function where we can scale down 0.5 now. So we don't even need these. So what I'm going to do is I'm going to go ahead and wipe these back to 1. Give me 1 second. Okay, so now all these are 1. It should scale all the way up to be as big as my screen, and then it should scale down. That looks really dumb. I'm not going to do that anymore. You understand. You see what I'm trying to do. Let's just do the scale. Actually, let's just do the scale. Scale works. We'll leave it at that. Just because it'll grow and shrink. It'll look kind of cool. You can speed it up if you want. You can make it look jiggly. You can do whatever you want. Oh, look, it flips. Ooh, because it's negative and positive. So that's kind of interesting as well. So hope you liked this episode. Maths. It's fun. I promise. We're going to get into a lot more mathematics as we go along. So get hyped about it. Freaking like what you're doing because this is a blast. Hope you enjoyed this episode. If you did, like it, subscribe it, comment it, do your thing. I look forward to hearing from you. Thanks for watching.